Good day everyone. In this presentation, I'm going to take you through all the problems on flotation from exercise 3 in Captain Subramaniam's textbook, Ship Stability 1. Let's start with problem number 1. A rectangular log of wood, 8 meters long, 2 meters wide and 2 meters high, floats in fresh water at a draft of 1.6 meters with one face horizontal. And we have to find its mass and relative density. So firstly, given the data that we have in the problem, we find the volume of the rectangular log, that is equal to length into breadth into height, and that works out to 8 multiplied by 2 multiplied by 2 equal to 32 cubic meters. The weight of the log is equal to underwater volume multiplied by the relative density of the water displaced. Now, the underwater volume is that volume which is below the water, and in this case it is at a draft of 1.6 meters. Whatever is underwater at a draft of 1.6 meters, we will calculate that. So that works out to underwater volume length into breadth into a draft of 1.6 multiplied by the relative density of fresh water, that is 1, and that gives us equal to 25.6 metric tons. We know the density of the log will be equal to mass divided by volume. We have calculated the mass above to be 25.6 and the volume also we have calculated above to be 32 cubic meters. Thus we get the density of the log to be 0.8 metric tons per cubic meter. Now relative density is a ratio between the density of the substance to the density of fresh water having the same volume. Therefore, relative density of the log is equal to density of the log divided by density of fresh water, and density of the log is 0.8 metric tons per cubic meter divided by density of fresh water is 1.1 metric tons per cubic meter. The metric tons per cubic meter in the numerator and denominator cancel out, and we have relative density of the log equal to 0.8. And relative density, being a ratio, has no units. Moving on to problem number 2. A rectangular log of wood, 5 meters by 1.6 meters by 1 meter, weighs 6 metric tons and floats with its largest face horizontal. Find its draft in salt water and its relative density. So volume of the log will be equal to length into breadth into height. That works out to 5 into 1.6 into 1 cubic meters. Weight of the log is equal to 6 metric tons. That is given to us in the problem. And relative density of the water in which the log is floating is salt water. Now weight is equal to underwater volume into relative density. Weight is given to us as 6, and in the underwater volume, length into breadth into draft. What is known to us is length and breadth, the draft is unknown, and the relative density in which the log is floating is salt water, therefore 1.025. Thus we see this is equal to 8.2 multiplied by the draft. Therefore, the draft is equal to 6 divided by 8.2 equal to 0.732 meters. Remember, always 3 places of decimals when you are calculating drafts, heights, distances. Density equals mass divided by volume. Mass is 6 metric tons and volume is length into breadth into the height. 5 into 1.6 into 1, and that gives us 0.75 metric tons per cubic meter. Relative density is equal to density of the log divided by density of the fresh water. Therefore, relative density is equal to 0.75 metric tons per cubic meter divided by the density of fresh water is 1 metric ton per cubic meter. So from the numerator and the denominator, metric tons per cubic meter cancel out, and we have relative density of the log is equal to 0.75. We move on to problem number 3 now. Problem 3 states a rectangular log 3 meters broad and 2 meters high floats with its breadth horizontal. If the density of the log is 0.7 metric tons per cubic meter, find its draft in water of RD 1.01. This is the information that is given to us in the problem. Area of the rectangular log is breadth into height, that is 3 meters by 2 meters. Density of the log is given to us as 0.7 metric tons per cubic meter, and we have to find the draft in water of RD 1.01. Density equal to mass upon volume. Therefore, mass of the log is equal to volume into the relative density. Volume is length into breadth into height. L is the unknown in this. Breadth and height are known, 3 meters and 2 meters respectively, and the RD of the log is known, 0.7. Therefore, the mass of the log works out to 4.2 multiplied by the length in metric tons. Therefore, mass of the water displaced is equal to underwater volume at a depth equal to D, draft equal to D meters, multiplied by the relative density of the water. In this equation, we have length is unknown, breadth is 3, draft is unknown, and relative density of the water in which the ship is floating is 1.01. Therefore, the mass is equal to length into 3 into D into 1.01 metric tons. Now we can equate the mass that we have calculated here with this mass. And when we equate the two masses, we find 4.2 multiplied by the length on the left hand side is equal to length multiplied by breadth multiplied by the draft multiplied by the relative density. Lengths on both sides cancel out, and we have the draft is equal to, in the numerator 4.2 and in the denominator 3 multiplied by 1.010. Thus we get draft equal to 1.38 meters. So draft in water of RD 1.010 is equal to. Problem 4. Problem 4 states a cylinder 2 meters in diameter and 10 meters long floats in fresh water with its axis horizontal at a draft of 0.6 meters. Find its mass. So given to us in the problem is the diameter of the cylinder is 2 meters, hence its radius equal to 1 meter. Length is 10 meters and the draft is 0.6 meters as shown in the diagram above. Now, taking a cross section of the cylinder, we have the circle. The radius OA, OB and OC are all equal to 1 meter. The chord AB, the length of this chord is what we have to find out. So let us take the point where the radius and the chord intersect, it be point D. If we find AD or BD, we can double it and say that the chord AB is equal to either twice AD or twice BD. To find AD, we use the Pythagoras theorem. We know that the radius is 1 meter and it is floating at a draft equal to 0.6 meters. That is, CD is equal to 6 meters. Therefore, OD will be equal to 0.4 meters. After we find the value of the chord AB, we need to find the value of the angle AOB. To do that, we can first find angle AOD or angle BOD and multiply it by 2, and you will get the sum of the two will be equal to angle AOB. OC is bisecting angle AOB. So let's see the solution on the next slide. Taking triangle AOB, AD is equal to the square root of AO square minus OD square. AO is equal to 1 and OD is equal to 0.4. So taking the square root of these two will give us the value of AD is equal to 0.917 meters. Thus, the length of the chord AB is equal to 2 times AD, and that is 2 times 0.917 equal to 1.834 meters. Now we take the sine of the angle AOD. AOD. Sine of the angle AOD is equal to opposite upon hypotenuse. We have calculated above AD is equal to 0.917 and hypotenuse is the radius, that is equal to 1. Therefore, sine of angle AOD is equal to 0.917 divided by 1. And when we calculate the value of angle AOD equal to 66.5 degrees. You double it and you have angle AOB is equal to 66.5 multiplied by 2 equal to 133 degrees. Now we have to compare the circle with the sector AOBC. We have to compare the circle with the sector AOBC. Therefore, area of the sector AOBC divided by the area of the circle is equal to angle AOB divided by 360. 360 being the angle that is subtended by the circle at its center O. So area of the sector AOBC is equal to area of the circle pi r square multiplied by angle AOB divided by 360. Since the value of pi is not given to us in the problem, we have to use 22 upon 7. Radius is 1, so 1 square. Angle AOB is 133 degrees, which we have calculated above. 66.5 multiplied by 2, and we divide the numerator by 360. Thus, we get the area of the sector AOBC is equal to 1.160 square meters. Now, we know the area of the sector AOBC and we can calculate the area of the triangle AOB. Area of the triangle AOB is equal to half base into height. Thus, half base is 0.917 multiplied by 2 equal to 1.834, and the height is equal to 0.4 meters. Thus, the area of the triangle AOB is equal to 0.367 square meters. Now that we know the area of the triangle AOB and we have already calculated earlier area of the sector AOBC equal to 1.16. From that, we deduct the area of triangle AOB equal to 0.367 and we get the area of the underwater segment ADBC. ADBC. This is the underwater segment. That is equal to 1.160 minus 0.367 equal to 0.793 square meters. Now this area of this segment multiplied by the length will give us the volume, and that volume is the underwater volume. Thus the underwater volume is equal to area of segment ADBC multiplied by length. Area being 0.793 we have calculated above, length being 10 meters that is given up in the problem itself, and we get the underwater volume equal to 7.930 cubic meters. And we know that the underwater volume multiplied by relative density will give us the mass of the cylinder. Thus, we have 7.930 multiplied by 1 equal to 7.9 metric tons. One place of decimal is enough for calculating mass. Moving on to problem number 5. A barge of triangular cross section is 20 meters long, 12 meters wide, 6 meters deep. It floats in salt water at a draft of 4 meters. Find its displacement. So refer to the drawing on the slide on the right hand side. You have a barge of triangular cross section whose length is 20 meters, 12 meters wide. It is divided into two parts at the point G, center of this breadth AB. So each section is equal to 6 meters and it is 6 meters deep. Now we know that the centroid of the triangle lies at 1/3 from the base or 2/3 from the apex. And since it is not given to us in the problem, always the triangular shaped object has to be with apex downwards and the base on the top. Unless it is specifically mentioned in the problem, always the base will be on top and the apex of the triangle will be down. So the centroid of this triangle shaped body, barge, will be located at 2 meters from the apex, 2 meters down from the apex, and 4 meters up from the base. Also given to us is that the draft of this triangle shaped body at which it is floating in the water is equal to 4 meters. The draft at which this triangle shaped body is floating at 4 meters, and this red line here denotes the water line at which this triangle shaped body is floating. So let us consider two similar triangles DFC and ABC. We have to now find the value of DF, the length, the breadth of the water line. So how do we do that? We compare similar sides, that is AB upon DF, or let us take it the other way around, DF upon AB equal to EC upon GC. Out of these four, only DF is unknown to us. So therefore we have DF divided by AB is equal to EC upon GC. DF therefore is equal to 12 into 4 divided by 6, and that gives us equal to 8 meters. Area of the triangle DFC is equal to half base into height. Half multiplied by the base, that is 8 meters, which we have just calculated, and the height equal to 4 meters as I explained earlier, giving us an area of 16 square meters. To find the underwater volume, we multiply this area of triangle DFC with the length of the barge. So 16 into 20, which is the length of the barge, gives us an underwater volume equal to 320 cubic meters. Displacement is equal to underwater volume multiplied by the relative density. Underwater volume we calculated here is equal to 320 cubic meters. Relative density is given to us as salt water, as that of salt water, so we multiply underwater volume 320 by 1.025 and we get the displacement equal to 328 metric tons. Cylindrical drum of 1.2 meter diameter and 2 meter height floats with its axis vertical in water of RD 1.016 at a draft of 1.4 meters. Find the maximum mass of the lead shots that can be put in it without sinking it. Now here, what is required of us in the problem is to find the maximum mass of lead shots that can be put in it without sinking it, which means that the top of the cylinder should be at the water level. That means it is still floating. But if we put in slightly more than what is required, this cylinder will sink to the bottom. Given to us in the problem, height is 2 meters, draft is 1.4 and it is floating in water of relative density 1.016. Diameter is 1.2, thus the radius is equal to 0.6 meters. Mass of the cylinder when fully submerged, that is without sinking, is equal to pi r square h multiplied by the relative density. And that is equal to pi being 22 by 7, r is 0.6 multiplied by 0.6 again, h is 2 meters, it is floating in water of RD 1.016, and that gives us the mass of this body to be 2.3 metric tons when it is floating at the top of the cylinder being at the water level. The mass of the cylinder at 1.4 meters will be equal to pi r square h multiplied by RD, and here we have to put the value of h as 1.4 and we get the mass of the cylinder when it is floating at 1.4 meters equal to 1.6 metric tons. The difference between 2.3 metric tons and 1.6 metric tons will give us the mass of the lead shots that can be put into the cylinder when fully submerged without sinking. Now it is important to note here is that it does not matter whether you put lead shots or steel or even water. All that is required is the difference between the two masses when it is fully submerged and when it is floating at a certain draft. Problem number 7. A rectangular barge 10 meters long and 5 meters wide, floating in salt water at a draft of 3 meters, is being lifted out of the water by a heavy lift crane. Find the load on the crane when the draft has reduced to 1 meter. The problem states the area of the rectangular barge is equal to length into breadth, that is 10 by 5, and RT is 1.025. The mass of the barge or the displacement of the barge when floating at a draft of 3 meters is underwater volume at 3 meters multiplied by RD. Underwater volume being length into breadth into draft multiplied by RD, and that gives us 153.8 metric tons. The mass after being lifted by the heavy crane to 1 meter draft is equal to underwater volume at 1 meter draft multiplied by the RD of the water in which the barge is floating. Thus, 10 multiplied by 5 multiplied by 1 multiplied by 1.025 equal to 51.3 metric tons. The difference between these two, the displacement at 3 meters and the displacement at 1 meter, will give us the answer. That is the load taken by the crane when the draft is 1 meter equal to 153.8 minus 51.3 equal to 102.5 metric tons. Problem number 8. A rectangular box 2.4 meters long, 1.2 meter wide and 0.8 meters high floats in water of RD 1.012 at a draft of 0.2 meters. Find the maximum mass of salt water that can be poured into it without sinking it. As I told you in problem number 6, it does not matter whether it is lead shards or steel shards or water. What matters is some weight is put into it till it sinks down to its maximum height. So, as we see in the diagram, it is floating at a draft of 0.2 meters. Its height is equal to 0.8 meters. The mass of the rectangular box at 0.8 meter height will be equal to length into breadth into draft multiplied by RD, that is 2.4 multiplied by 1.2 multiplied by 0.8 multiplied by RD 1.012 equal to 2.3 metric tons. Mass of the box when floating on even keel at a draft of 0.2 meters will be equal to 2.4 into 1.2 into 0.2 into 1.012, which is the RD of the water in which it is floating, gives us 0.6 metric tons. And the difference of 2.3 metric tons and 0.6 metric tons lets us know how much salt water can be put in the rectangular box when it is fully submerged. That is 2.3 minus 0.6 equal to 1.7 metric tons. Problem number 9. A box-shaped vessel 18450 metric tons displacement is 150 meters long and 20 meters wide. Find its draft in salt water. Information given to us in the problem is this. Displacement is equal to underwater volume into relative density. Underwater volume is equal to length into breadth into draft, and therefore displacement is equal to length into breadth into draft into relative density. Out of all this, the only unknown is the draft. 18,450 metric tons is the displacement, length is 150, breadth is 20, and the relative density in which the body is floating is of salt water 1.025. Thus the draft is equal to 18450 divided by, in the denominator you have 150 by 20 by 1.025, and you get the draft equal to 6 meters. Going on to the last problem, problem number 10 in this exercise. A box shaped vessel 120 meters long and 15 meters wide is floating in dock water of RD 1.005 at a draft of 5 meters. If her maximum permissible draft in salt water is 6 meters, find how much cargo she can load now. She is floating in dock water of RD 1.005, and you have to find the maximum permissible cargo that can be loaded when she is floating at 6 meters draft in salt water 1.025 RD. This information is given to us in the problem. So, displacement at 5 meter draft in RD 1.005 equal to underwater volume multiplied by RD. Underwater volume is length into breadth into draft multiplied by RD, and that gives us 9,045 metric tons. Maximum displacement she can load in salt water at 6 meters is equal to length into breadth into draft, which is given as 6 meters, multiplied by RD of salt water, gives us 11,770 metric tons. The difference between these two, 11,070 and 9,045, will give us the cargo that can be loaded, and that is equal to 2,025 metric tons. Thank you very much for your kind attention. I hope I have been able to solve your problems to your satisfaction. Give me a thumbs up, like, share, as well as subscribe to my channel, and you will get information as soon as new videos have been posted. Goodbye.